Hello everybody, this is Dr. Bricker here with a video for Chapter 18. So we went from Chapter 25, now we're going to Chapter 18, which is ray optics. It might seem strange for you, but if you remember the end of Chapter 25, we looked at electromagnetic waves. So really it's light waves, and by light I mean the whole spectrum from radio waves all the way up to gamma rays. So it just depends on the frequency of the waves as far as the energy goes. As you know from Chapter 25, all these waves travel at the speed of light, 3 times 10 to the 8th meters per second. But depending on what these waves interact with, different properties come out. So in Chapter 18, ray optics, we're going to look at objects that behave like rays when they go through things like lenses, interact with mirrors, bounce off different surfaces. Sometimes it's appropriate to look at these waves behaving like a ray of light. Then we're going to actually go back to Chapter 17 and look at light behaving like a wave, interacting with things really small. The wave properties of light come out. And then when we go into modern physics, we could actually look at light as actually sort of being like a particle. So that's the reason for going from 18 to 17, and then we'll actually go back up to the modern physics section and then look at light sort of behaving like something called like a photon, behaving sort of like a particle that has mass. Okay, good. So let's get started with this. Okay, so goal of this chapter: understand and apply the ray model of light. So we're going to have things called diffraction, reflection, rays going through, interacting with mirrors, going through lenses, that sort of thing. So it's kind of a long chapter, actually. Something called Snell's law. Okay, so light rays can bounce, or in other words, reflect off a surface. So your geometry skills are going to come into play in this chapter. So rays from the bird's head reflect from the water, forming an upside down image. Now, if you think of it, if we were all standing around this pond looking at this bird, we would all be able to see the bird at the same time. It's because light is reflecting from the bird and also reflecting from the water in all different directions, so we could actually see the same thing at the same time. We don't usually think of that. It's really quite amazing if you stop and think of it. The only reason that, say, we're looking at this duck and we're all around the pond looking at it, we all can see the same thing at the same time. And really it comes down to light is hitting the bird and the water, reflecting in all different directions and hitting us all in the eye. Okay, so we'll learn about the law of reflection in this chapter. Okay, 2 images of the turtle are due to refraction. So reflection is light bouncing off a surface. Refraction, it's important to know what terms mean. It means the bending of light when it goes from one medium into another medium. So, light might go from air into water, and then it's going to bend. So Snell's law governs this. Okay, rays refracting at surfaces of this lens form a magnified image. So the second part of the chapter we'll look at spherical mirrors and lenses. Okay, probably won't get to that in this video, but it's coming up. We'll experience something called the lens maker's equation, which actually works for lenses and for mirrors. Okay, so the ray model of light, which ignores diffraction, is valid as long as an aperture through which the light passes are larger than 1 millimeter. Okay, so this is when light actually behaves like a ray. When it starts going through small openings, then it starts behaving like a wave, and you get all sorts of interesting phenomena that come on. If you send light through a really small hole, it's not going to just end up on the wall behind it in one spot. It's going to actually spread out, something called diffraction, and we'll see that in Chapter 17. So for the time being, this is kind of a disclaimer. Going through large openings, 1 millimeter or greater, light is going to behave like a ray. Okay, so a light of ray is a line in the direction along with the energy is flowing. So, this light does have an electric field part, does have a magnetic field part. We're just looking at the direction that it's moving. But the whole time it does have the electric field and magnetic field part. It's just if we look at these large openings, we don't see that behavior come out. Okay, so a laser beam is a good approximation to keep in mind when you're doing this. Whoops, went too far here. So light travels in straight lines. It travels at the speed of light unless it enters something else. So the speed of light in a medium is given by the speed of light divided by n. So n is the index of refraction. So in air, n is about 1, so the speed of light is close to what it is in a vacuum. Not exactly, but really, really close. if light goes through, say, water, it slows down. The speed is less in water. The index of refraction of water is about 1.3 or so. So light travels slower through water. And then that's the reason that you see it bend. Okay? Light rays can cross and they don't interact with each other when they cross. A few things to keep in mind. So this is reflection. Light comes in, hits a surface, and bounces away. This would sort of be like, you might think of it like a mirror or something like that. Refraction, on the other hand, light comes in this way, and then it bends. So this is going from one medium into another. A couple of other things, scattering, light going in all different directions, or light going into a medium and being absorbed, the energy being absorbed. Okay, so we'll look at really kind of cases of reflection and refraction. Not too much with scattering and absorption, practically speaking, in terms of working out problems, but reflection and refraction definitely. Okay, so here's a tree. An object is a source of light rays. Either it could be reflecting light from other sources, or it could be emitting light itself. The reason that when we're in a room together you can see me, it's not that I'm emitting light of a certain wavelength that you can see with your eyes. I'm reflecting light. If we turned off the light in a room, you would not be able to see me if it was really completely dark. Now, there is a way to see me. You'd have to have infrared goggles on. I do emit light, but it's infrared, so it's lower energy than visible light. And you would be able to pick that up. But in terms of visible light, I'm reflecting visible light. That's why you can see me with your eyes. Okay. So diverging bundles of rays hit the eye. This is supposed to be the lens of the eye. And then they form an image on the back of your eye. And your brain processes that and flips it back over. So we don't see things upside down. Our brain processes it and flips it back up. But really, when the image hits the back of your eye, it's upside down. Okay, so all these different lights, different rays come together at one point. So this ray is going this way, hits that part of your eye. This ray goes that way, hits the lens. Different part of the lens refracts it this way, etc. And eventually they come back together, and that's how we can see this object. This is the image that it forms. Okay, so this is the image. This is the object. Okay. So self-luminous objects directly create light, and humans don't create visible light, they create infrared light. So things like light bulbs or the sun would be a self-luminous object. Most things that we see are because light has been reflected, though. Okay. So a ray source, this is a good way of thinking about this, is a laser pointer. This gives you a nice ray. It's a way of thinking about these rays, where they're actually coming from. Okay, so a point source like this has light going in all different directions. It's small, light goes in all different directions. If we were all in a room together, we could see this light because it's going in all different directions. You can't see a laser until it hits the wall. You don't actually see it moving unless somebody shines it right in your eye. This source, on the other hand, you can see because it's going in all different directions. Okay, this is a larger surface. So you can think of this as being made up of a whole bunch of point sources, so a so-called extended object. Okay, so typically when we do these problems, we don't have to look at every single spot of this light. I mean, you might look at the bottom and the top and then infer what's going on after that. Okay, so parallel light sources, say from a star or something like that, come from really far away. So if they actually hit this, maybe this is probably the sun actually, they come from far away, the ones that actually are going to make it here must be ones that are really parallel. If not, they would end up out here or down this way. So by the time they get here, they're essentially parallel, just like this flashlight source. So a ray diagram is a diagram that shows a few of these. So again, you're not going to do a diagram for every single spot on this tree. You might look at the top and the bottom and then see how it interacts with a mirror or a lens or whatever you're talking about. Okay? So seeing objects. In order for our eyes to actually see an object, the light has to hit your eye. So if you're looking at this laser, you can't see it. Sometimes you can if somebody throws dust in the path of the laser, and then light is reflected in all different directions, and then you can see the laser beam. But if I just took a laser beam and shined it on the back wall, you wouldn't see the light going through to the back wall. You would just see the spot on the wall. Unless it hits you in the eye, you don't see it. Okay, so point source, extended sources emit light every different direction, and then again, that's the reason that we can all see the same thing at the same time. Take that for granted, but that's really quite amazing. Okay, so diffuse reflection is the process of reflecting incident light in all different directions. So here's an incident ray, and here's another one, goes in all different directions, and then we can see it. These are just some definitions. Scattering, these are related to each other, is a process at which single rays are broken into many weaker rays and leave in all different directions. So here's a ray, it comes into the spot, goes in all different directions. That's called scattering. And this whole process is diffuse reflection. Okay, so almost the same thing, really. So if you read a book, maybe we're both reading a book, looking at you have a test question, I come over, you ask the question, we can both look at the question at the same time because of this idea that light is hitting and going in all different directions. Okay. So lasers are only visible if it actually hits you in the eye, but if you threw some dust or smoke particles, it says here, you could actually see the laser beam because light's hitting it and scattering in different directions. Some of the light hits you in the eye. So shadows are where light doesn't hit. Sometimes they kind of overlap and you get completely dark regions, or then you get gray regions where some of the light gets but not all of it, and then some completely illuminated areas. So an opaque object, this means light doesn't go through it, can intercept rays from a point source leaving a dark area. So here's a point source, light goes in all different directions. So from here, light's going up here, hitting this area. Maybe from the bottom, none of it gets up there, right? It just goes over here, so you can have a shadow form then. Okay, and then over here, not too much. So this is a completely dark shadow. This isn't the case where you might have a gray region, because light from here would go there, light from down here would go here. Everything else is blocked because it's a point source. But you could imagine if this is larger, not a point source but an extended source, if light came from the top, it maybe wouldn't make it here, but maybe from the bottom, if it's really big, light would make it in here, that sort of thing. So that's how you can get gray regions, as this picture shows. This is a better picture actually than what I just did. An extended source is large enough of a large number of point sources, each casts its own shadow. So different parts of the bulb, let's just look at the top versus the bottom. Light comes from the top, light comes from the bottom. Maybe light coming from the bottom does not get to A, but light coming from the top does get to A or B or C. So that's how you can get sort of gray versus completely dark areas. Okay, so depending on the size of the source, there's often a true shadow that no light reaches, and then you can get the case if it's big enough that maybe some of the light gets there from the bottom but not the top, and that's how you can get kind of grayish areas. Okay. So here's an example problem. I made a separate video going over the homework questions, so take a look at 18.1 instead. This is actually the first homework problem on homework 7, so take a look at that homework help video. So reflection. Specular reflection is the reflection from a nice smooth surface, like a mirror, for example, or a piece of polished metal. You can make a mirror out of polished metal. Just get some polished metal, put some glass in front of it, and you have a mirror. I once made a mirror, so I live in an old house, changing out the windows. I got a window. It was an old one, replaced it with a modern one. It was really leaky. So instead of throwing it away, I painted the back of it with silver paint. They actually make spray paint that you can make glass into mirrors. So I took my old window, I spray painted the back with this reflective paint, covered that with a coat of protective material, and I made my old window into a mirror. It's not a great mirror, but it looks pretty cool, and it's, you know, about 150 years old or something like that. that. So it works really well. So anything that is a smooth surface, nice piece of polished metal, that sort of thing. So my piece of glass, the back side of it, I painted it. It was nice and smooth, and you can see yourself in it. Okay. So here's a couple of definitions. Here's an incident ray. Here's the surface. Here's the reflected ray. And this is where I said a little bit with geometry. You'll rely on your geometry background. The angle of incidence is equal to the angle of reflection. And these, with optics, always measured from the normal to the surface. So that's the normal to the surface. Normal means 90 degrees. So this incident angle is equal to the reflected angle. Be careful, sometimes problems will give you like this angle here, which is perfectly good. You just don't need that angle for optics. You need the angle measured from the normal. Okay, so a single light ray represents the entire bundle of parallel rays that are coming in, but we can just write it as just a ray. So this one comes in, leaves. So the angle of incidence is the angle between the incident ray and the perpendicular to the surface. As you can see, there's the normal, or in other words, perpendicular. There's the angle of incidence, that's this one. This is the angle of reflection, that one. Okay, so those are equal to each other. So this is the law of reflection. Incident angle is equal to reflected angle. So you'll have to brush up on your geometry skills, maybe not. So this problem is similar to 1811 on the homework. We have a full-length mirror over here on the right-hand side. This is 2 meters. This is a ½ meter. And then we've got 1 meter over to a light bulb. And let's see what we have here. Full-length mirror, closet door, 2 meters tall. The bottom touches the floor. A bare light bulb hangs 1 meter from the closet door. Okay, so here's the light bulb up here. And they give us some different dimensions. So this is 1 meter from the door. This is a ½ meter down to the top of the mirror. Okay, good. How long is the streak of reflected light across the bottom of the floor? Okay, so the longest it's going to be is when it comes from the top of the mirror. If a ray came here in the middle, it would end up somewhere over here, which is perfectly good, but we want to know what's the longest ray. So the longest ray is when it hits the top of the mirror. Okay, so the angle of incidence, that's this angle here. Actually, let me switch to the pen mode. This is the angle of incidence. This is the angle of reflection. And they are actually equal to each other. And this theta here is the same as this theta. I think these are called opposite interior angles or something like that. So just from some geometry, this angle is equal to that angle. It would be like this case. Okay, so this angle is equal to this angle, some geometry. That's why the one here is equal to the one there. Okay, so the book goes through and solves this. I think I came up with maybe an easier way of actually solving it where you don't actually have to get the angle. So let's take a look at that. Okay, so this is how I want to solve it. I'm going to just look at, let's see if this is working. Yeah, there we go. I want to look at this triangle. So the little one up there that has, we've got theta, it's 0.5 meters high and 1 meter across. Basically, it's this one. I'm looking at this triangle, and then I'm looking at the triangle down here, this big triangle. And I noticed, you know, they both have theta involved, so the triangles are similar to each other. So if I did the tangent of theta from this one, so tangent of theta from that one has to be equal to the tangent of theta of the larger one. So tangent of theta is equal to opposite over adjacent, so 0.5 over 1, and these are all in meters. The tangent of theta from the lower triangle would be tangent of theta, whoops, get rid of that. I'm not sure why that did that. Okay, for some reason it freaked out a little bit. So going back to the upper one, it was the tangent of theta is 0.5 over 1. That has to be equal to the tangent of theta from the lower one, which is equal to 2, that's the opposite side, that's this side, divided by the adjacent side, which is L. Okay, and then we can solve for L from this. L would be equal to 2 times 1 divided by 0.5. This is all in meters. So 2 divided by a half would give us 4 meters. So the author of the book solves it one way, where he actually figures out what theta is and then gets the length. This way you don't even have to actually get theta. So it's a little bit cleaner. Same idea though. That's where this is coming from. But again, you don't have to get theta. It doesn't ask you for what theta is. It asks you for what L is. So follow through there and you'll see, I think my way's better. It's quicker anyway, maybe not better. Okay, but it's using some geometry. I just used the tangent of theta. They used the little triangle to figure out theta, and then knowing theta, then they figured out the length. But that's okay. I avoided that middle step. Okay, so let's take a look at this one. You are looking at the image of a pencil in a mirror. What do you see in the mirror if the top half of the mirror is covered with a dark piece of paper? So we'll need a ray diagram for this one. So I'm just going to show you what this diagram looks like, because it really helps out here. So here's the mirror covered with some paper. Now we've got to look at these rays and see what happens. So again, we're not going to look at a ray from every single point on the mirror. We're going to look at the top and bottom. So from the top of the pencil, the light would come in and reflect this way. Angle of incidence is equal to angle of reflection for that ray. Let's look at the ray from the bottom. And I'm just looking at the rays that will hit me in the eye. This ray comes this way, hits, and then this is the normal. Angle of incidence is equal to the angle of reflection again. So these rays hit me in the eye. So why do I see a mirror? Well, my brain traces this back. And to my brain, it seems like the image is here. Okay, so it's something called a virtual image. It's not, the pencil's not really in the mirror, but your brain thinks that it is, right? If you look at yourself in the mirror, your brain thinks that you're inside the mirror, and the image is upright, just like the pencil is upright here, and it's virtual. Okay, so full image of the pencil. Even if you cover up the top, you're still going to see it here. It's the rays that actually hit you in the eye that you see. Okay. So on a microscopic scale, the surface of a diffuse reflector is rough. Okay, so it might look something like this. The law of reflection holds, but these rough surfaces of the surface cause the rays to leave in all different directions. Okay? It still obeys the law of reflection, it's just it's going in all different directions then. So a plane mirror is just a flat mirror. A plain old flat mirror, I guess. Rays from point P will reflect according to the law of reflection. So here's the object. Light leaves the object. This is normal to the surface. Incident and reflected ray angles are the same. Same thing here. You can do this for all of these. So these rays all look like they're going back in different directions. Now, if you wanted to, if say your eye was over here, here's your eye. You could sort of trace all these rays back and see where this is actually coming from. Okay. All right, this slide is actually got a better picture than me trying to draw it. So here's the object. Light comes in, it's reflected, and you can kind of trace it back. Light from this object goes this way. Incident and reflected rays are the same, and you can trace it back. This is where the actual object would be formed. You know, it looks like it's in the mirror. Okay, so S is the object distance. S prime is the image distance. So for plane mirrors, S and S prime are always equal to each other. Okay, we'll have to get some more practice with that. So point P prime, from where the reflected rays diverge, is called a virtual image. Okay, so whenever it's the image, there's your eye. See, this is a lot better picture than the one I was drawing. So this ray comes in, it's reflected, another one comes in, reflected. They hit you in the eye, but your brain traces it back, and this is where the image is appearing. So it's virtual because you have to trace the rays back. The rays aren't actually coming from there, it just appears that they're coming from there. So it's a virtual image. Okay. Your brain doesn't know the difference, though. A lot of magic tricks are based on mirrors, and you can imagine why. I mean, if you think about it, we're just so used to looking at a mirror, we don't really think about sort of the magical aspect of that, right? I mean, there's an actual image, and it looks like you're in the mirror. Okay. So, as I said before, S prime is equal to S. The object distance and the image distance are the same. And here's the mirror, and then you can see the other half of the person reflected in the mirror here. Looks like they're floating, right? In real life, what's happening is the person is standing there on one leg that you can't see because it's behind the mirror, and when you see the image from this side, it looks like the person's just floating. Okay, so, I mean, if you were at a magic show, you saw somebody floating, maybe it has something to do with this. Okay, so plane mirror, the eye captures and focuses diverging bundles of rays from each point. And again, we're just looking at the top and bottom of this object. So coming in again, reflecting to the eye from the top. Same thing's happening at the bottom of the tree. And then it appears to your brain that the light's coming from inside the mirror. Okay, so rays from each point on the object spread out in all directions and strike every point on the mirror. And we're just looking at a few of them here. I mean, in real life, it's coming from all different points. Okay, so here's an example. If your height is h, what is the shortest mirror on the wall in which you can see your full image? Where must the top of the mirror be hung? So let me read it again. If your height is h, so you're h tall. Okay, so here's the top of your head. Good. What is the shortest mirror? So what's the shortest mirror on the wall in which you can see your full image? And where must the top of the mirror be hung? Okay, so your guess might be if you want to see your whole self, the mirror has to be as tall as yourself, but that turns out to not be true, and we'll see it with this problem. So we use the ray model of light to solve this. And remember, you need the light to enter your eyes to be able to see. So to see at the top of your head, the ray from the top of your head would have to hit here and then go into your eye. Now the ray that comes from your foot would have to hit the bottom of the mirror and then end up in your eye. So it would have to be something like this. Okay? Now we'll have to actually figure out how big this mirror is. So there's a few things here. L2 is the distance from the floor to your eyes, and then L1 is the distance from your eyes to the top of your head. Okay? So if it's L1 from the top of your head to your eyes, halfway between there is 1/2 L1. Okay? And then, again, if this is like, this is the normal to the surface, that's cutting it in half. If it's L2 all the way to the top of your eyes, this would have to be 1/2 L2 then. So let the distance from your eyes to the top of your head be L1, as I said. To your feet are L2. Your height then is L1 plus L2. That's from your feet to the top of your head. A light ray from the top of your head that reflects and enters your eye must be this distance, 1/2 L1, for that to actually happen. And then same thing, this is kind of a summary of what I've already said. The distance from the ground to your eyes is L2, so this distance has to be 1/2 L2, and that one has to be 1/2 L2 for the ray from your feet to hit the bottom of the mirror and then hit your eyes. Okay, so the shortest mirror in which you can see your full self is 1/2 your height. So if you have a mirror that's half of your height, you can see your entire body, as long as it's half the distance from your top of your head to your eyes hung down. Okay? And also it says here, interesting that the answer does not depend on how far you are from the mirror either. You might think, I'll just keep moving farther away and then I'll be able to see myself, but that's not how it works. Okay? Very good. You could work out that situation if you want to. You see that the distance from the mirror doesn't matter. So refraction, on the other hand, then, is the bending of light. So the first part of this chapter is reflection, really, and then from a plane mirror, and then refraction using Snell's law. And then really the second half of the chapter is using the lens maker's equation. So two things happen when light crosses the boundary between air and glass. So part of the light reflects. So here's the incident ray here. Part of it reflects and part of it refracts. Part of it goes back through here. And you can see when it goes back through here, it bends. And then when it goes back to air, it bends again because it's going from glass back to air. So it bends again. And then part of the light continues into the second medium. It's transmitted rather than reflected. Okay, so here's the reflected part. Here's the refracted part. So refracted means enters another medium and is bent. We'll have a law called Snell's law to figure out how much that is bent, depending on what it enters. Okay, so this figure shows the refraction of light from parallel beams like this. So these all come in, they're all going to bend the same. Here's light coming in at different angles and then bending differently. These remain parallel to each other. These are going in different directions. Okay, reflections usually, it depends on what it is, but smaller than the refracted amount in these pictures. Okay, so here's the incident ray. Here's the part that's reflected, and it says weakly reflected. It's some still is. Here's the angle of refraction. So angles are always measured in relative to the normal. So here's the normal to the surface. Here's the normal to the surface. So here's the incident angle. Here's the refracted angle. So when you go from a lower index of refraction, like if this is air, and you enter glass or something, the light is bent towards the normal. Okay, so light comes in, it's bent towards the normal. When you go from a lower index of refraction to a higher index of refraction. Okay, works in reverse as well. Here's an incident ray in medium 2, hits the boundary, and then it's refracted this way, so away from the normal. So this index of refraction here in medium 2 is higher than the index of refraction here. Okay, good. Here's Snell's law that governs this behavior. N1 sine of theta 1 is N2 sine of theta 2. So 1621, imagine what was going on in the world then. Dutch scientist Wilbrord Snell, never realized his first name was that, proposed a mathematical statement of the law of refraction, and here it is. Okay, so this will depend on how much light is bent when crossing the medium. There's a table in the book too that has different indices of refraction. Okay, so here's one we can take a vote on. Remember, you were looking at the normal to the surface. So here's the normal to the surface. So this angle, we're comparing that angle to that angle. So if light's going this way, it's bent away from the normal. This would be like going from water into air. Okay, so N1 must be bigger than N2 for this to actually happen, because light's being bent away from the normal. Okay? If you don't want to memorize that, just write it down on a piece of paper, draw a picture, and have that little note there. Remember, you get to make your own formula sheet, put whatever you want on there. Here are some indices of refraction then. So in a vacuum, exactly 1. In air, actual, accepted. So actually it's this. So light doesn't slow down much in air. But usually we just use this, right, in class. Water's 1.33, oil 1.46, typical glass 1.59, cubic zirconia 2.18, diamond 2.42. So if you want to develop a test to determine if what you have is actually a diamond or cubic zirconia, see how much it bends light, and that's a way to actually do it. Maybe you can't tell just by at a far distance, but if you set up an experiment, you could determine based on how much light is bent. Silicone 3.5, infrared it says here. Okay, so the higher N, the bigger the index of refraction, the more light is bent towards the normal if you're going from, say, air into that material. Okay? So when light is transmitted into a material with a higher index of refraction, it makes a smaller angle with the normal, so it's bent towards the normal. When light is transmitted into a material with a lower index of refraction, maybe you're going from glass to air or something like that, it makes a larger angle with the normal. Okay, so to analyze these different problems, and you'll have to get some experience with this, draw a ray diagram. Don't forget, we're always working with the normal to the surface. Okay, label the different angles that you have. You have Snell's law to work with, but you also have geometry to work with. Okay, and just be careful that you're actually measuring the angles relative to the normal. Here's a quick check. Light rays enter a glass prism as shown. Which is a possible path for the ray through the prism? Okay, so you have to see if it makes any sense. We're going from light into glass. So think about those. You're going from light to glass. You're going from air to glass. Light is going from air to glass. And then it's going again from, say, glass back to air. And you have to look at the normal to the surface to see if any of these situations make any sense. So let me draw your attention to D here. So here's the normal to the surface. Here's the normal to the surface. Okay, so does this one make any sense? When light goes through the prism here, the angle here should get smaller, as it does, from here to here. And then when light is in the substance, now we're going into air. Here's in the substance, and then here it gets larger. So D actually makes sense. So go through the other ones and convince yourself that it's not A, B, and C, but it has to be D for that reason, right? When you go from air to glass, we're going to bend towards the normal. See if that happens with all the other situations. I mean, C is the one where obviously it bends way away from the normal, right? So, do the same thing with those other ones, and you'll see you get the same incorrect situations. It's got to be D. Okay. Okay, so here's an example. We've got air and we've got plastic. These are supposed to say degrees. So light comes in this way in air, and now we've got plastic here. First of all, these are perfectly good angles. They're just not the angles that we need to solve this problem. So for example, this is the angle of incidence. This is the angle of refraction. Right? So normal to the surface is 90, so if this one is 45, the other one has to be 45. And let me call this one like theta 2, and I can call this one theta 1. We're just going to say that this is 1 because it's air. And then let's go back and see if we've got plastic in our table. Plastic 1.59. And 2 is 1.59. Okay, so we've made the adjustment. We put the angles that we need to solve this problem. Up here in air, here's what we have. Down here in plastic, here's what we have. So we can then use Snell's law. N1 sine of theta 1 is equal to N2 sine of theta 2. Whoops, sine of theta 2. Then we have everything. The only thing that we're looking for, oh, wait a minute. What is the index of refraction of plastic? Okay, let's not assume that we know this. Let's just see if it comes out to this actually. Question mark. That's what we're trying to figure out. Okay, so then I'll write it up here. N1 sine of theta 1 divided by sine of theta 2 is equal to N2. Okay, so you put the numbers in and see what you actually get for this one. And then you can compare it to the known value from the book. Okay, that's the way to use Snell's law. We have a special case called total internal reflection, and it occurs when light is unable to refract through a boundary. Instead, 100% of the light reflects. This is the idea behind fiber optics. So let's look at this tank. Here's light that comes in. What color do we have? Red's good. This ray comes in, goes this way. It's going from water to air. This ray comes in. Okay, it refracts here. This ray comes in. None of it actually passes through. All of it is refracted. The extreme example would be this. Light comes in, you get to something called the critical angle, whoops, and all of it goes this way. Okay, so this is called the critical angle here, theta critical. That's where all of the light is none of it leaves. Total internal reflection. Okay? We can solve it the same way. Let's call this one n critical, this n1 or whatever you want to call it, and then this is 90 degrees. Right, because we're measuring it relative to the normal. So what we're going to see in a minute, it's really just Snell's law. It's a special case where this theta 1 up here is 90 degrees. Okay, and this only happens when n critical is bigger than n1. So you have to go from a higher index of refraction to a lower index of refraction. You can get this total internal reflection idea. Okay, this is a better picture than what I've done, but it's the same exact idea. Okay, so that's a summary of what I've said. So this is what you get. So use Snell's law and solve for theta critical. The critical angle is the inverse sine of n2 over n1. There is no critical angle the other way around. This only happens when you go from like glass to air. That's what fiber optic cable actually does. And you can solve for that critical angle. So that's kind of a neat idea. You shine light through, say, a pool or something like that, and none of it gets out if you're at the critical angle or greater. Yeah, I should say it's critical angle or greater. I mean, if you shine light at even an angle like this, that's definitely not going to get out, right? Okay, so the critical angle or bigger than the critical angle. Okay, and that's the idea behind total internal reflection. So light's not leaving. So binoculars use a pair of prisms forcing the light to undergo two total internal reflections before emerging from a light piece. So light's coming in, and we want to keep it all here. Goes through a prism, it all stays in the prism, goes through another prism. Here's the first one, here's the second one. So all the light then enters your eye through another lens. Not all binoculars are like that, but this is a way that you could actually do that. Okay? Excellent. So here's a quick check. A laser beam undergoes 2 refractions plus total internal reflection at the interface between medium 2 and medium 3, which is true. Okay, well, we know because there's total internal reflection here, that only happens when n2 is bigger than n3. That's a piece of information that we know. What can we tell from here? Here's the normal to the surface. My picture's not that great. Eraser. Okay. Pen. Okay, so you kind of have to look at this. It looks like this angle here, I'll call that theta 2, measured from the normal. We have to compare that to theta 1. We have to decide if it's bending away from or towards the normal. And to me, it looks like it's bending away from the normal. So I would say n1 is bigger than n2, just because it's bending away from the normal down here. So this ray is bent away from the normal compared to this ray. Okay. So putting these all together, looks like this is the one that actually works out. N1 is bigger than N3. Well, I know N2 is bigger than N3, and N1 is bigger than N2, so finally N1 must be bigger than N3. And that's what we have there. Okay, excellent. Okay, we've gone through almost 70 slides today, so why don't we leave it there for today. Hopefully you're working on homework 7. Questions that you have, we can set up a Zoom, whatever you want to do. Talk to you soon.